Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is a continuation of a review for college algebra students who are just entering into a college algebra course. A lot of the content here is assumed prerequisite material. In fact, it is prerequisite material. However, this is such key information for success in college algebra and then in calculus that it's important to have this high-level review. Although, if you saw my last video, you'll note that I took my time with it, so it wasn't so high level. In this video, we're going to talk about rational exponents. So we'll start with this definition here of a rational exponent. As long as it is well defined, that means that it exists, the nth power of the nth root. Let me highlight that because it sounds like I'm saying the same thing. The nth power of the nth root of a number a, which is written as the nth root of a to the nth power. Or, by the way, it could be written as the nth power of the nth root of a. They're equivalent statements. So the index of the radical and the exponent on a can move in and out of those parentheses. Anyhow, that notation, that radical notation, is much easier denoted using the rational exponent notation a to the n over m. That is because it's much more common to work with rational exponents in calculus and all of mathematics rather than radicals. Radicals are kind of antiquated. In fact, they go by the wayside just like mixed numbers go by the wayside. There's not a lot of people in mathematics that do stuff like this. Oh, 3 1/7, right? Not a lot of people work with that. They work with fractions like 22/7. Oops, other than making my ink mistake there. They work with this type of fraction, an improper fraction, 22/7. So it is very important that you let go of ancient notation, in this case with this sub-example that I'm giving, the mixed number notation, but in the case that we're talking about now, radical notation, you should be able to exchange that quickly for rational exponent notation. And my little statement right here, that is the nth root of a to the n, which is the same thing as the nth power of the nth root of a, is all equivalent to a to the n over m power. Again, there's one huge caveat here. The huge caveat is as long as it is well defined. That is critically important. It is very, very easy to lose the fact that something's not defined when you switch to rational exponent notation. So this is important to kind of make that note. So let's start by simplifying this statement right here. And I just want to let you know, you want to not work with radicals when you're working in high-level mathematics. In other words, you do not want to exchange this out, although it is equivalent, you do not want to exchange this out for the third root of this messiness, okay? You just don't want to do that because it makes the mathematics harder for you in the long run. One thing you do want to be aware of is that with an exponent, if you have a rational exponent like this is, the numerator of the rational exponent is the power, and the denominator is the root, or the index, I guess you could say, of the root. And although we're not going to use that in this example, I just want to remind you that that is the case, that that's what that notation means. The numerator of the exponent is the power, the denominator is the index of the radical. All right, let's go back to this problem here. We're being asked to simplify that statement. The very first thing you should do when asked to simplify is follow the order of operations. The order of operations is all about going to the innermost group. So if you look at this statement, The innermost group is this x plus y. You're looking for grouping symbols in its innermost group. And by the way, another tactic, especially with fractions here, is to focus solely on the numerator first, clean that up, then move to the denominator, clean that up. So if we did it that way, I would focus in on the numerator, and I'd say, okay, well, let's see what we can do to the numerator to clean it up. And the reality is nothing. The numerator, negative 27, x to the 6th, y to the 1st, does not clean up at all. However, the denominator might. So let's take a look at the denominator. We have an x plus y in a quantity, and then a y to the negative 2. Following the order of operations, you would say, can I clean up that x plus y first? And the answer is no. So I'm just going to rewrite that x plus y. Again, following the order of operations, I will ask myself, is there a better way to write y to the negative 2? And the answer to that is, heck yeah. We totally know a law of exponents, and I'll write that off to the right-hand side. If you have a number raised to the negative nth power, that is the same as 1 over that number raised to the positive nth power. Likewise, if you have a number 1 over b to the negative nth, that is the same as b to the nth over 1. So this little statement of y to the negative 2 right here, that can be written as either 1 over y to the 2, or you could just quickly think of it this way. Well, I see I have a y to the negative 2 in my denominator. I can move that into the numerator with a positive 2 as its power. So that's what I'm going to do here, is I'm going to move that y to the negative 2 upstairs to have a positive exponent of 2. Again, this is something you should recall just from your laws of exponents from your pre-algebra or elementary algebra courses. All right, continuing forward, I now reassess the situation. Can I simplify that numerator? Yes, I can. I have y to the first times y to the second, that's y to the third, so I'll just write that in here. Negative 27, x to the 6th, y to the third, all over. Downstairs, I just have an x plus y. Notice I didn't bother writing the parentheses on that. There's no need. It's not multiplying anything other than 1. Now that I've completely cleaned up the numerator and I've completely cleaned up the denominator, I'll go ahead and now step outside of these big parentheses here, step outside of this highlighted area, and look at the exponent and apply that exponent to my arguments within my base there. So one thing that I'm going to be using here is another law of exponents. B, or maybe I should write this as a over b. A over b to the mth power is the same thing as a to the mth over b to the mth. That's a law of exponents, one that you should be incredibly familiar with. So we're going to go ahead and take a baby step here. A lot of people do this all at once. I'm just kind of reminding you of stuff, so I'm taking my time. So, but this will be a negative 27, x to the 6th, y to the 3rd, raised to the 1/3. And downstairs, you have an x plus y in a quantity raised to the 1/3. Nothing huge there. And now we'll go ahead and do one more law of exponents. A times b raised to the mth power is a to the mth times b to the mth. That is, if you have a product of factors, in this case negative 27 times an x to the 6th times a y to the 3rd, all being raised to a power, you can apply that power to each of those factors. So that's what we're going to do. This becomes a negative 27. I'm going to zoom out slightly just to make it easier for me to write, to the 1/3 power. You have an x to the 6th, again, to the 1/3 power. And you have a y to the 3rd, one more time, to the 1/3 power. And this is all over that quantity x plus y to the 1/3. Before we continue, I do want to mention something that's critically important. A plus b raised to the nth power is not a to the nth plus b to the nth. Addition and subtraction are the first operations you learn in mathematics, but they're the worst operations you learn in mathematics because a lot of the things that you think should be true with them are not. We would love it if a plus b to the nth power was actually equal to a to the nth plus b to the nth, but that's not going to be the case. They are not the same. And you can easily see that if you just take an example like a plus b squared. That's the same thing as a plus b times a plus b, which is the same thing as a squared plus 2ab plus b squared, which is definitely not a squared plus b squared. So there you go. That's a simple example as to why this red statement up here is not true. All right. So we cannot distribute, in quotes, this 1/3 power to that x plus y. It's just going to sit as a power on x plus y. There's nothing you could do about that. Then we move forward and we deal with all of these exponents upstairs. So the third root of a negative 27 is a negative 3. We do know that. So let's go ahead and write this out. This is a negative 3. I'm using a law of exponents here. The law of exponents that I'm using now is b raised to the m, then raised to the nth power is b to the mn. So powers to powers multiply is what I often say in a class. So that x to the 6th raised to the 1/3 is actually x to the 6th times 1/3, or x to the 6/3. Write that in there. But there's no real reason for me to leave that as 6/3. We know that's x squared. And y to the 3 times, or raised to the 1/3 is y to the 3/3. But again, no need to write 3/3. We could just write it as a first, and no need to write a 1 in an exponent. We just leave it as the silent 1. And then downstairs, we have this quantity x plus y and quantity to the 1/3 power. And guess what? That's it. That's completely simplified. There's nothing else you could really do other than possibly rationalizing the denominator. But as I've mentioned in the previous video, I do not rationalize denominators if there's only a single term down there. And there is only a single term in this denominator, so there's no need to rationalize it. You may look at that and say, no, I see two things, an x plus a y. Yeah. But that's within the 1/3 power. So that whole thing is a briefcase or a suitcase of one object. If I had plus 10 here, then I would go ahead and rationalize the denominator, but I don't, so I won't. There you go. This is completely and totally simplified. So in this next example, what we're going to do is simplify and write this answer using only rational exponents. However, you don't have to do it in the order that they're stating here. You do have to kind of learn as you move forward in mathematics to do things in an order that is best for you, to be honest with you. And so what I'm going to do here is I'm going to rewrite everything in terms of rational exponents first, and then I'm going to simplify. That's just a habit that I have. You don't have to go about it that way, but I'm letting you know that's what I'm going to do here. I'm going to list out all the properties I'm using as well. The very first property that I want to use is I want to use a property that allows me to break apart all these radicals. So that property is a property of radicals themselves, and it looks like this: the square root of a times b, or the nth root, or whatever it is. In fact, maybe I should go ahead and say that. I'll write it out. If a and b are non-negative, then the nth root of the product of a and b can be broken apart into the nth root of a times the nth root of b. And that's what we're going to do for each of these radicals. I'm just going to break them apart into their component forms. Remember, this expression we want to say is equal to something, so I'm going to say that's equal to. Again, I'm breaking this up: the square root of 128 times the square root of x to the 10th times the square root of y to the 15th minus 4 times the fourth root, be very careful about that, of 2 times the fourth root of x to the 20th, and then times the fourth root of y to the 29th. And finally, plus 2xy. And again, we have a square root of 2 here, we have a square root of x to the 8th, and a square root of y raised to the 13th power. That's a lot of rewriting there, but very powerful rule to use. Now we're going to go through each of these expressions or terms one by one and transform them. And personally, I like to use very special notation here, which is the rational exponent notation. So I'm going to trade out all of my variable statements. Specifically, let me go ahead and highlight them. This guy, and I'll go ahead and highlight all of them. All these variable statements right here, I'm going to trade them out for rational exponents. The constants, like the square root of 2 and the fourth root of 2 and the square root of 128, I will leave in radical form. However, I'll reduce them if I can. For example, the square root of 128, well, that's the same thing as the square root of 64 times 2. I'll write that in there, root 64 times 2. Otherwise, again, I'm going to use the property or the definition that the nth root of a to the n, let me write that in. So the nth root of a to the n is the same thing as a to the n over m. So I'm going to go ahead and trade out all that highlighted ink for that. Remember, square roots are index 2. It's just a silent 2 that's right here. So that x, the square root of x to the 10th is actually x to the 10 halves. Write that in. We know that that's going to be 5, but I'm just taking my time with it. Y to the, we'll have y to the 15 over 2. Minus 4, we have a fourth root of 2 attached to that. Let me go ahead and move this over, fourth root of 2. We'll have an x to the 24ths, a y to the 29 fourths, and then plus 2xy. Let's see what we got going on here. Square root of 2 doesn't really change very much. We have x to the 8 halves and y to the 13 over 2. So it looks kind of terrible, but it does simplify quite a bit. For example, the square root of 64 times 2 is 8 times root 2. 8 root 2. X to the 10 halves is x to the 5th. Y to the 15 halves, I'm actually going to leave it like that for the time being. We're going to talk about what to do in a moment. And then we have a minus 4 times the fourth root of 2. X to the 5th, again, y to the 29 over 4. And then finally, plus 2xy, root 2. Then we have this x to the 4th, y to the 13 halves. And by the way, we can do a little bit of compression of terms, especially on that last one, right? This guy right here, you have an x to the 1st times an x to the 4th. Those will combine beautifully. And you have a y to the 1st times a y to the 13 halves. That will combine beautifully as well. So I'm going to go ahead and do one extra little move here to go ahead and clean that up. And I also want to note something here. When you're working with radicals, it's often best to write the radical as the last factor in the list. So I'm going to write this as 8x to the 5th, y to the 15 halves. And then I'll write the square root of 2. The reason why that's a good habit to get into is because a lot of people end up elongating this radical until it ends up covering everything it shouldn't be covering. So you can really avoid that by writing radicals on the back end. And that's what I'm doing there. Let's see, we have minus 4x to the 5th, y to the 29 fourths. And we have this fourth root of 2. And then we have, let's see, positive 2. We'll have an x to the 5th because it's the first times a fourth here. And, or first plus a fourth, I should say. And then we have y to the 2 halves plus or times y to the 13 halves, which will be y to the 15 halves. And then we have this square root of 2 hanging off the back. Now we get down to this point and we say, I don't think we can combine anything because it looks like an absolute mess. But you actually can combine terms here. If you take a look at pictures, I have 8 of these x to the fifths 15 or y to the 15 halves root 2's, and I have 2 more of these x to the fifth y to the 15 halves root 2's. So altogether, I should have 10 of those. I have 8 of them up front, 2 of them as my last term, so I have 10 of those altogether. Those 2 terms will combine beautifully. So I'll write that as 10 x to the fifth y to the 15 over 2. And again, we have that root 2 hanging off back. And the only thing that's left over is that little 4 times x to the fifth y to the 29 over 4, and then 4th root of 2. And those 2 terms will not combine at all because, well, they can't combine. They're not identical. They both do have an x to the fifth, don't get me wrong, but the y's they don't have in common. Y to the 15 halves is not the same as y to the 29 fourths. So those 2 terms will not combine beautifully. Now going back to the instructions, let's just see. Simplify and write the answers using only rational exponents. Technically, we have not finished this because that square root of 2 is not written in terms of rational exponents, so we might as well do that. Let's go ahead and rewrite that square root of 2 in terms of rational exponents and the 4th root of 2 in terms of rational exponents. And when you do that, you do not have to leave that 2, wrong pen color, you do not have to leave that root 2 on the back end. You can actually move it right next to 10 when you do that. I'll showcase what I mean. So this is going to equal, we have a beautiful 10 times 2 to the 1/2, because that's the square root of 2, and then x to the fifth and a y to the 15 halves. That's that first term written only with rational exponents. And then minus 4 times 2 to the 1/4, because that's what the 4th root of 2 is in terms of rational exponents. And then x to the fifth, y to the 29 over 4. And really, as far as simplification, there's not much else you can do. Now, some students will ask, do I have to factor this? No, I didn't ask you to, but you could if you wanted to. It's not really going to be super helpful here. Well, actually could be, but they're not asking us to do that. They're not saying simplify and factor. They're just saying simplify. So I would probably leave it just like this, personally. But in future topics, we might end up needing to factor that. Now, as a final statement here, I like to kind of dive into the whys. Why does something work? Why does something not work? So let's go ahead and talk about a big mistake that a student often does make. They say that the square root of x squared plus y squared is equal to x plus y. I want to be incredibly clear here. This is not a true statement. This is not true. But what I'm asking here is, let's list out as many reasons as possible as to why, in general, that is not true. It is true in like 3 cases. It's true when x and y are both 0. There's one case where it's true. It's true when x is 1 and y is 0. It's true when y is 1 and x is 0. It's actually true when x is 0, but y is non-zero, as long as y is positive. And it's true if y is 0 and x is some positive number. So there are actually, I should say, a lot of cases where it is true, but in general, there's an infinite number of cases where this is false. So the question is, why? And the very simple answer that I'll often get from students is that, well, you can't break apart a radical. And that's true. You can't break apart a radical. So the very first reason why this is not true, is that you cannot break radicals across addition or subtraction. That is the square root, my pen's going funky here, square root of x squared plus y squared is not the same as the square root of x squared plus the square root of y squared. You cannot break radicals across addition or subtraction. Now, multiplication and division, often you can, but addition and subtraction, you cannot. So, but that's not really a great reason. Like, that's just a justification why it doesn't work. But a lot of people just memorize that justification. It's not enough, really, for me. Another thing you can do, though, is if somebody makes a claim, they say, I swear this is true. If they're saying something is true, they are saying that it's true all the time. And all you need to do is provide one counterexample. That's all you really need. One single little counterexample. So let's go ahead and invent a single little counterexample. We're going to let x equal 3 and y equal 4. If you let x equal 3 and y equal 4, you'll get the square root of 3 squared plus 4 squared, which is the square root of 9 plus 16, which is the square root of 25, which is beautiful 5. If this statement here were actually true, then it should be the case that 5 is equal to x plus y, x being 3 and y being 4. And we would then have proven that 5 is equal to 7, but that is not the case. So there is a counterexample. So that's a wonderful way to showcase that something is not true. It's very often how people argue. When somebody tells you, I swear this is true, just look for the counterexample. That usually will obliterate any part of their argument. And if they say, well, okay, that's just one situation, well, then you could say, but if I can present one situation, then I could possibly present an infinite number of them. So do not tell me something's always true if it's not always true. Okay, so what's another reason why this is not true all the time? And probably the most obscure reason, I think, for students is the Pythagorean theorem. Now you might think, wait, why is he bringing Pythagorean theorem into this? It's not even a triangle. And you're right, it's not. However, I do recognize this statement, square root of x squared plus y squared, as the result of the sum of the sides of sum of the squares of the sides of a right triangle. So if I gave you a right triangle and I said, hey, this side length is x and this side length is y, we know by the Pythagorean theorem that this hypotenuse has to be of length square root of x squared plus y squared. Well, great. But how does that tell us that square root of x squared plus y squared cannot equal x plus y? Well, this is more visual in this case, so I just want to showcase it here. If I were to look at this length y, and I were to try to create, let's see if I can do this. If I were to try to say, okay, well, this is that same length y right there, you could see from here to here, if that's of length y, and we have this length x down here, and we're to say, okay, well, let me see if that square root of x plus y is the same as the length y plus the length x. Well, if I were to try to attach to this a length of x, it's much longer than x plus y, that is. It's much longer than the square root of x squared plus y squared. So visually, it does not work out either. So that's just a little kind of an interesting approach to doing this. It's not exactly a proof, but it's a great justification visually. Now, there are several other ways to showcase that this cannot be true in all cases. Most of them boil down to the first two here. You can't break radicals across addition and subtraction, and also you can provide a counterexample where this is not true. However, I would love to see in the comments if somebody has an idea of why this is not another reason why this cannot be true. There are some really creative ways to showcase this, but anyhow, these are just some of them. And I like this idea of asking, why do you think this is not true, and having you answer. All right, that does it for this lecture, or review, I should say. Not very much of a lecture, but a review on rational exponents. I'll see you in the next video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at ease. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.